So the battery has revolutionized, the world. This was the first type of electricity that they had, back before the battery. All they had was static electricity. Can't do a whole lot with that. But once the battery was created, a whole number of experiments were able to be performed with electricity, and that's where, the work of Michael Faraday comes, and Maxwell and so many others that had a huge influence on our understanding of electricity and really revolutionized our world with and using electricity now. Um, Volta was able to create a cell by using chemicals, and we're going to unpack what's happening with that here. Let's say that we had, a carbon electrode and a zinc electrode and sulfuric acid. Now, thankfully, we're not using sulfuric acid as an electrolyte. We're using other substances, but we need something acidic that can, make one of the metals corrode, and we'll see how that works here. So first, the acid slowly dissolves the zinc electrode. The zinc electrode, it's getting worn away. Some of the zinc atoms are actually leaving and going into the sulfuric acid. What happens is the atom goes into the sulfuric acid and then leaves two electrons behind. So that atom is actually in here, and then atom, and then you have two electrons stay behind. The acid then becomes positively charged because of those atoms, those zinc atoms that go into the acid, and that actually pulls off electrons from the carbon electrodes. So the carbon electrons leave to make the atoms that went into the acid neutral, and that leaves the carbon electrode positively charged. And then now that it's positively charged, we have a potential difference. We have a positive side, we have a negative side. And then if we connect the two, like this, and let's say we have a filament here, and we connect the two, here's our light bulb, we're going to have light produced, right? And so the electrons are going to leave here, go through the filament, and then come through the other side. And then, the filament's going to get hot and then send out light. So, you've probably seen batteries, there are cells that look like this, that are starting to wear away. Some of that acid is leaking. Some batteries are pretty nasty, and, that's a big issue. What should engineers, researchers do about these chemicals, in the batteries? And so some of the things that they're considering, or that they have done over the years, is use materials that are less harmful to the environment. It used to say, on batteries, proper disposal techniques for that. Now it's a little bit better, but it's still an issue and it's still something that should be considered. So you may remember with J.J. Thomson, the cathode ray tube experiment where he discovered the electron. And this was a big deal. He discovered the electron. It really paved the way for our future understanding of the atom, and paved the way for folks like Rutherford that came along and found that the atom's mostly empty space with his gold foil experiment. What anodes are and cathodes are, they're two different sides of an electrical situation. So the cathode ray tube, right, shot off electrons. And so that's probably the best way to remember this. The cathode itself shoots off electrons. If that's true, then it's the negative side. So negative voltage, cathode side is negative. And so therefore the anode side is the positive side, and that hopefully could be a good way for you to remember which one's which. So if we think about it, right, with a cell, inside the cell, the zinc gives off positive ions and keeps electrons, right? So if we think about it that way, it shoots off positive charge inside. And, so inside there, right, you're actually shooting off positively charged atoms. However, you're leaving the electrons behind. So if we look at it externally, right, externally we just see the electrons leaving this and going into our, light bulb or whatever here. So considering that, right, and externally, it's a cathode, right? It's sending out negative charge. But if you wanted to be technical and say, okay, inside what's happening, you could consider it an anode. Okay, with cells, charges need to be pushed, right, to go in the same direction of a conductor, and that's what the electric field does. And once you set up the electric field, you can evaluate that in terms of potential difference, the voltage inside, and you've got that. So you have to have that electric field. Batteries convert that chemical energy into electrical energy, and we've seen that, with the example here with the zinc and carbon electrodes with the acid. Batteries are composed of more than one cell. So what we looked at before was actually a cell because, it's just one set of or two pieces of metal and then the acid inside. A battery is more than one cell in series. And so the EMF, the electromotive force of a battery, is the sum of the EMF of the cells that we would add up. So, in a typical flashlight, you see something like this. You have, two cells back to back, the positive terminal, the negative terminal touching here. And so the current was going to flow through the entire thing, all the way through. And this adds up to, let's say each of these was 3 volts. Let's say this is 3 volts, this is 3 volts. You'd have a 6 volt system there. Typical AAA, AA's, they're all about or 1.5 volts. And, those ones that have, the boxy looking one with 2 prongs, it's not a symbol, right? They just tell you it's a 9 volt, right? That's because it's got a lot more voltage. So the EMF of a battery is the work done per unit charge, moving a charge from one terminal to the other. And so this is a important definition that you'll need to remember. Work done per unit charge in moving the charge from one terminal of the battery to the other. And so, this is what we talked about with potential difference. And with current flow, you have to have that potential for current to flow. And so the amount of current that we have is directly proportional to how much voltage we have. We have more voltage, we're going to have more current. And so, the greater the difference, the greater the potential difference, the greater the current will flow. Just like if you had a greater height difference, with a pipe and water going through it, you're going to have faster flow. And, there's always going to be resistance, right? So the current's going to try to go through, but there's going to be resistance, trying to hold that current back. And that actually has to do with the atomic structure of, the substance that it's going through. But yeah, again, the voltage is again directly proportional to current. So these collisions that they have within the wire, right? The electrons are accelerated by this electric field. They're sent through. They hit atoms along the way and slow down, right? And so these atoms that they hit along the way, depending on the substance, you're going to interact a little bit differently. These atoms then vibrate and with increasing kinetic energy. And so these atoms, right, as they receive these electrons, send out the electrons, are vibrating with more energy. And, the electrons get accelerated again and hit more atoms. And, as they continue through those, the whole, wire starting to get hotter because it's shaking, it's getting, all these collisions. And the temperature will increase within the wire because of these collisions. So one of the things that you'll definitely want to remember is the factors that affect resistance. Length is the first one that we'll talk about here. The shorter the wire that you can have, the less resistance it'll have. That's because it doesn't have to travel as far of a distance. The electrons don't have to travel as far of a distance for the current to make it all the way through. The longer that wire is, the longer that path is, and the more resistance that you'll have. The thicker the wire that you have, the better. And so the thicker wire that you can have, there's more room for those electrons to pass through than it is for a small wire, and the resistance will be greater. Materials, copper is a great conductor, right? But aluminum, even though it's a metal, is not as good of a conductor. Those electrons aren't going to transfer as easily and has more resistance. Temperature, the higher the temperature is, the greater the resistance. That's because those atoms are moving around more quickly with those collisions, and it's more difficult for those electrons to pass through without, interacting with particular atoms and colliding with them. The lattice ions is another important idea here. We'll go ahead and read this here. If a free electron traveling from atom to atom in the crystal lattice encounters an irregularity in the lattice, then its path must deviate to navigate past the irregularity. That deviation can be considered as resistance and is usually caused by collisions of the free electrons with other core metal ions in the lattice. And so this is a picture here of different situations. If you have an additional atom inside the structure, the lattice is kind of affected there. The missing atom, the lattice of the particles there is kind of tight there. A small atom, substituting for a metal, right? So these being all metal atoms, let's say you had a small atom within there, it's going to affect the lattice as well. Or if you have, a large atom inside the metal lattice, it'll look like this. And so that electron, as it tries to pass through, it's going to encounter this and will slow down. It's going to cause resistance. The current will slow down because of it, and we look at that as an increase in resistance. All right, so now we get to one of the most important equations within electricity, Ohm's law. This relationship is very critical for our understanding and being able to predict what will happen with circuits and what will happen with current, with voltage. Ohm, back, this is 19th century, he did some significant work, and he discovered that metal conductors have a certain amount of resistance based on their properties. However, it doesn't matter how much voltage you put on it, it's going to have the same resistance. And this was a really important idea because, the actual atoms within within a metal, and the as a collection in a metal conductor, the resistance will stay the same. And so current then is inversely proportional to resistance, and that's an important idea as well here, where if you increase the resistance, let's say you double the resistance, you're only going to get half the current. And so it's a combination of both of these things. The fact that current is inversely proportional to resistance and resistance is independent of voltage allows this relationship to work. And this is a linear relationship. If we look at the combination of voltage and current, we double voltage, we should double the current. We triple the voltage, triple the current. If we double the resistance, we'll have half the current. If we triple the resistance, we'll have a third of the current, and with the same amount of voltage. So let's draw a circuit here. We have a cell. This is how we draw a cell, a long side and a short side. The long side represents the positive terminal. The short side is the negative terminal, and we have a ohmic motor, we'll say. It draws 600 milliamps, 1.5 volt battery. We're going to find the resistance of the motor. And then for part B, the battery becomes weak, or the cell becomes weak and produces only 0.9 volts. How would the current change? So because it's ohmic, once we find the resistance, it doesn't matter how much voltage we have on it, it's going to stay the same resistance. And so, yeah, why don't you go ahead and try this one. Go ahead and pause the clip and give this a try, and then when you're ready to check, you can hit play to continue. All right, so V equals IR. We have our voltage and we have our current, and so the resistance then will be 2.5 ohms. And for part B, we keep the same resistance, 2.5 ohms, and we have the voltage, which is 0.9 volts. we divide that out. So the current that goes through the circuit would be 0.36 amps then.